Okay, so my little step 3 here is going to be that for any, so epsilon here you can fix it, you know, like 0.1 or something. I mean, but this works for any epsilon. Well, you know. But for the argument, you're just going to fix some fairly small epsilon. And R is sufficiently large. There exists a K, right? So remember, we were looking at this speeded up random walk where we just look at every kth step. So there is a K, so that the probability that, you know, you pick the step between xi and xi plus 1. You know, so, you know, you have your speeded up random walk and you have xi and xi plus 1. What's the probability that that's R persistent? It'll be close to 1. Okay, that's somehow I think that's maybe what does the trick. So the probability of the set of omegas, so that omega ki x naught, omega ki plus 1 x naught is R persistent, is greater than 1 minus epsilon. Okay, so it's a fairly large probability that your arbitrarily chosen, I mean, step between xi and xi plus 1 looks just like this. Okay, so there are sort of 3 points here. The proof consists of 3 bullets. The first bullet, so we need to know, first of all, that the distance between xi and xi plus 1 is at least 3r, right? So the distance from xi to xi plus 1 is greater than or equal than 3r by, or with probability, I should say, with probability converging to 1 as k goes to infinity by what? By step 1, right? That's the that was the fact that your the distance from x0 goes to infinity with large probability, right? So if I increase the number of steps, then the distance from my initial point, which is here xi, right? I'm thinking of random walk starting at xi and then running k steps and asking what's the distance between the base point and the kth step. Well, as k goes to infinity, the distance goes to infinity. So this will be true, right? As long as you make k big enough. The second bullet is so that xj greater than I or I plus 1. So I want to worry about this. You know, I want to think about the points that follow xi plus 1. I want to make sure they don't come back into this half space. I want them to stay inside this half space. So that this don't intersect, right? A distant half space has probability converging to 1 as r goes to infinity, right? R is the distance here. Between xi plus 1 and this half space that I don't want to hit, the distance is r. If this r is big, then the probability that I'm going to that I won't hit it is going to be as close to 1 as I like. That was 2. And in the third bullet, now I want to say something about this. I want to say that the ones that precede also don't, they don't enter here. So that, okay, does anybody know what I'm going to say here? How do I know that I'm allowed to go back in time? That xj less than I don't hit a distant half space has probability converging to 1 as r goes to infinity by 2 also, but applied to the reflected measure. So I want the random walk that goes back in time rather than forward in time. So and this is the random walk of the reflected measure. Measure mu hat of g equals mu of g inverse. Right? If you do a random walk with respect to this new measure, that's like going back in time with respect to the old measure. And so, for the same reason, you're not going to, it'll be unlikely that this path going backwards will enter this half space over here. So you have these three kind of events whose probability is close to 1, and so that means that the intersection also has probability very close to 1. And that means that this thing is persistent. Okay. Okay, we're almost done. Yes.
We're using the fact that mu is non-elementary.
Oh yeah. So mu hat. I want to know that mu hat is also. I want to know mu hat is non-elementary. Yeah.
It's not necessarily a symmetric measure.
That's true. Yes. You have to. I want to know that mu hat is non-elementary as well. Okay, so now number 4 is, so this will make it clear why this concept is good. There is some constant c, so that if I look at the distance between x0 and xn, so this is xn is right. This is the same as omega n k applied to x naught, right? We're looking at this k-step random walk, and we get to xn. The distance is at least as big as c times n, or c times the number of r persistent segments xi plus 1, where r is r comes from number 3 here. So here we have so I'm fixing epsilon, and I'm fixing r sufficiently large, and I'm fixing k like in 3 here, so that these things hold. So for that r, there exists a c, so that this says that I'm making linear progress, because I have to convince you that the number of these persistent segments is also growing linearly. But remember, number 3 said that the probability that any randomly picked segment like this is r persistent is close to 1. So there will be lots of these persistent segments, and so that will mean that the distance is growing linearly. Okay, so why is this? Okay, so the proof is you look at so gamma is going to be a geodesic from x0 to xn. Okay, so here's my x0, here's xn, and here's the geodesic, and then I have xi somewhere. So maybe xi is over here, xi plus 1 is over here, and here's a persistent segment, and I have these half spaces like this, like in the definition of a persistent segment. So all of these points, all the xi and the previous points are in this half space, and xi plus 1 all the way to xn, they're all over here. Now half spaces are quasi-convex. So when you have two geodesics joining the 2 points, 2 pairs of points in these spaces, then they have to, in the middle, they have to fellow travel. So there is going to be a segment of length c over here. Well, maybe I'll draw it over here. There's going to be a segment of length c where c is, it's something slightly less than r. This distance here is bigger than r. There's going to be, in the middle, there's going to be some segment that fellow travels the segment between xi and xi plus 1. Because the real picture, right? The real picture is you have half spaces really look like this. And if I pick 2 pairs of points, here, and I draw a geodesic between these two and geodesic between these two, well, in the middle they're going to fellow travel. Right? This is like a tree. And so, okay, so I have these segments of length c between x0 and xn whenever I have a persistent segment. Now, all you have to notice is that these segments are pairwise disjoint. The next segment, the one that comes from, maybe there is a x, there's xj. There's going to be xj and xj plus 1 is maybe another persistent segment. And maybe j is bigger than I. So xj and xj plus 1 are both in this half space. So the corresponding segment is also going to be in this half space. Well, coarsely, it might pop out by a few deltas. But it'll occur disjointly along this geodesic from this segment here. So that's how you get this inequality. These segments are pairwise disjoint, and they're all placed along this geodesic from x0 to xn. So you see that the length must be c times the number of these segments, at least. Okay, so these segments are disjoint. Okay, so then we're just about done. So to finish the proof, we're just going to use the Kingman's subadditive ergodic theorem again. Okay, so now I want to finish the proof. So theorem. So there exists eta, so that eta positive, so that the lim n, the distance x0 and x0 divided by n is greater than eta for almost all omega. Okay, so let's prove that using those the steps that we have. Okay, so I'm going to define a function z and k. So k is just like in the over here. So this is fixed. I'm fixing small epsilon. I'm fixing r, k, so that this holds, and then this holds as well. I'm fixing the c. Okay, so this is all fixed now, and I'm defining this function zkn that goes from omega to r, or r plus, and this is just the number of persistent segments. So z and k of omega, this is the number of persistent segments. Oh, actually, let's see. Sorry. It's really omega k here, where omega k is the space of k-step paths. Right, this is the space of paths of the form. You start with 1, and then you have you have omega k, and then you have omega 2k, and so on. Right, it's not. It's the measure on this space is the measure that's induced by the k-fold convolution. It's like making k steps at the same time, and then. Okay, so it's the same set, but the measure is maybe a little different depending on this k. Okay, so z and k is the number of r persistent segments on x0 xn. Right, so I stop after n. After time n, which is really, there are k times n steps of the original walk, and I count how many r persistent segments I have on this interval between xi and xi plus 1. Right, so some of them are persistent, some are not, and I just count how many there are, and that's the value of this function. Okay, and this is subadditive. Right? Why is it subadditive? Well, I have, it's a random walk. So I have, it's x0, there's x1, x2. Some of these are persistent, some are not. But, so you can. So the point is that you can have if the second portion of the path, one between xn and xn plus m or whatever, if it sort of backtracks, right, then it might stop being persistent. Persistent means that all the points that come after xi plus 1 stay in this half space. But this is only between xi plus 1 and xn, really, right? Because we're measuring this between xn. But it could be that that after time n, they somehow violate this and they go back. So that's why you only get less than or equal. That's why it's only subadditive. Okay, so you're counting the number of persistent segments, and then what else do we know? What do we know about the integral of this function? What's the largest it can be, right? It can be more than n, right? There's n segments in total, so this function is certainly less than or equal to n. So zkn is less than or equal to n, so it's integrable. All right, its integral is at most n. So that's a good thing for Kingman, right? We need integrable functions. What else do we know? What do we know about? Is there a lower bound? So this is, I guess, the probability theory way of writing integrals. This is the expected value, right? Zkn. So this is the integral of this function over the space of paths. Okay, so what do we know about this? So I can think of it as this is the sum of pieces where I look at the ith piece and I assign either 0 or 1 depending on whether the ith segment is persistent or not. So this is the integral of y ik, where this is, so y ik is either 0 or 1. It's 0 if if this segment here is not persistent, and 1 if it is persistent, right? So this function is really just a sum. The zkn is the sum of these functions, right? So it's counting how many persistent segments there are. So the integral is the sum of the integrals, but each of these is greater than 1 minus epsilon. That's what number 3 said that I erased. The integral, the probability that the ith segment is persistent is close to 1. So I can make it greater than 1 minus epsilon. And so this whole thing is greater than n times 1 minus epsilon. Okay? Right? Because it's very likely that the ith interval is persistent. Okay, so Kingman now tells me that these functions zkn divided by n converge to some function zk infinity. Right? And not only that, but this function is constant, just like before. It's because u is still ergodic. This is still constant. But it's also positive, because this convergence is also, you also get convergence in integrals. The integral of this, if I integrate this, I get something bigger than 1 minus epsilon. And so in the limit, I also have to get something bigger than 1 minus epsilon. So this is certainly this constant is not 0; it's positive. Okay, and so now we have that. Okay, so what is the drift now? So lim inf of the distance between x0 and omega kn x0 divided by kn. So here I'm taking, for this fixed k, I'm really looking at every kth step, and maybe so I'm really looking at numbers here divisible by k. But for other, it could be 1 mod k or 2 mod k or something. But I just shifted random walk with this different starting point, so I won't worry about that. So let's just see what this expression. I want to claim it's positive, right? So this is using the fact that these distances are this is greater than c times the number of persistent segments, I can estimate this. This is bigger than this number c divided by k. I'm copying k over here, and then I'm writing lim inf of z kn over n. Right? This thing here is bigger than c times zkn. That's what my number 4 said. This is the number of persistent segments is zkn. And then I'm distributing k and n like this. But this is, but by Kingman, this converges to this number, which is positive. And so this is positive. Right. So this is it. This is the end of the drift. We now see that the drift is positive. Any questions? Any murky points?
So in the step 3, so you given epsilon, right? So you find for sufficiently large R. So that sufficiently large R should be given xi, and so you stay xi j, which is less than I, stay in this side and
Right,
side,
right.
right? So that determines what kind of R we should have, right?
Yes, yeah. It should be the probability of hitting this wall that's distance
So
r
given
should be
epsilon,
small.
You can make that the probability stay in that is 1 minus less
Right,
than
right.
equal to 1 minus epsilon. Then you determine k, so that that distance is greater than equal to 3r,
Right.
right? So you have to determine k later, right? Actually.
Yes, yes. Epsilon, I think epsilon
But
comes.
my question is whether that holds. So this has to hold for all I in that statement, right?
Yes, yes, it does. So this is.
But so there are and the k depending on.
So I think the logic is epsilon comes first. You fix some very small epsilon,
Right.
and then on the basis of epsilon you choose r, and then you choose k,
Right.
and you
But
just work with it.
So that sort of uniformly holds for all I. I mean, I is xi.
So number 3 was that the probability that the ith interval is r persistent is bigger than some. So that's uniformly now for every I.
For every I.
For every I. That estimate is independent of I. Because this is the point of taking the of looking at the random walk kind of infinite in both directions. I don't stop at n, right? It would be enough to say, well, just when you get to xn and you're still on this side, then you're happy. But I'm actually continuing the walk and going all the way to infinity, and my probability is estimating that the whole random walk stays in this over here. And likewise, over here, I go to minus infinity, and I'm estimating the probability that it stays on this side. That's why it's independent of I.
But also that C also should depend. I mean, if x, you have a path and let's see between x0 and xn, and so xn should be greater than any xi, right? So I mean that's
Yes. So it's
looks like it seems like depending on where that xi is. Right?
well. So so xi and xi plus 1, and then so they determine these half spaces, and I know that x0 is in this half space and xn is in this half space. And so that means that if I draw the geodesic between them, somewhere in the middle, say in the middle third or whatever. I mean, some deep in, maybe C is just r divided by 3 or something. In the middle, they're going to fellow travel each other, just because these half spaces are convex. If you take two convex subsets in a hyperbolic space.
No matter where that xi is in this half space.
Well, no, xi is going to be a distance at least r in this half space.
Right.
But x0 I don't know. X0 might be even on the boundary. And likewise xn might be on the boundary. I don't know where it is in the half space.
So
But it's still true. It's still true that they're going to fellow travel each other. Just because you have two.
True, right?
Yeah.
But that length c may. Also, how you get that c, that length?
Well, so it's just it's the distance. It's the distance. Shortest distance between the two half spaces, and then you have to subtract maybe 20 delta on each side. It's like okay. So let's draw the picture in hyperbolic space, in hyperbolic plane.
Depends only on the delta.
It just depends on delta, right?
Delta now.
Right. So it's a hyperbolic plane. So I have this half space and I have this half space, and then my xi maybe is here and xi plus 1 is here, and this is my geodesic. Now I don't know where x0 is. Maybe x0 is here and xn is here, but the geodesic between them still looks kind of like this. And in here, as soon as this distance here is 20 delta or something, then on the rest of the interval they're going to fellow travel each other. And these different intervals are going to be disjoint, because the next interval, when I go to some number bigger than I, the next interval will be inside this half space, so it won't be anywhere close to that one. So I don't know. I mean, I'm not sure if you guys are running out of energy here to listen. I mean, it's about 3 more pages to prove that pseudonosubs are generic. I don't know if you have patience to see all the. But maybe I'll just outline steps without proving them. How is that? That might be a good compromise. But you can. I mean, if you're interested, you can look at the paper. I mean, that part is fairly readable. It's just some elementary hyperbolic geometry. Okay, so I want to argue that so G is acting on X, and there's mu as before, and it's non-elementary. Then there exists L greater than 0, so that the probability that the translation length of omega n is less than Ln goes to 0 as n goes to infinity. Okay. Okay, so there are 2 lemmas, I think. There are 2 lemmas and 1 hyperbolic geometry fact. Okay, the first lemma is measure theory or something. It's both. I mean, I don't know. Okay, so in this situation, I take any, so L from n to n is any function that goes to infinity. L of n goes to infinity as n goes to infinity. So the point is, you should imagine some function that grows very slowly, like say log n. Okay, and that could be a function. Much slower than linear, for example. Okay, I'm going to write the conclusion, but there's going to be a piece of notation that I'll have to explain. So the probability that Wm inverse x naught dot um x naught. So this is the Gromov product. I think well, okay, let's see. It's less than or equal to L of n. This goes to 1 as n goes to infinity. Okay, so M m is going to be roughly n half. Okay, so m here is maybe the floor of n half. So if n is even, then I'll just take exactly half, otherwise I just approximate. So Wm here is G1, G2 all the way through, or Wn is G1, G2 all the way to Gn. And of course, Wm is the initial subword of length m. And then Um is going to be the rest of it. So it starts at Gn plus 1 and goes to Gn. And so the picture is you have x0 here, and then after m steps you have Wm x0. So the m steps you get here, and then you continue and you get to Wn x0 after further n minus m steps. So this is roughly the midpoint of the path. And the question is how close, you draw the geodesic between x0 and Wn x0. The question is how close is this point to the geodesic? Okay. And this estimate says it's pretty close. You know, the probability that the distance is less than L of n is pretty high. So I can, L of n has to go to infinity, right? It's not going to be that this is bounded distance away. That's not going to be true. But any slowly growing function like log n, the probability that you're less than that function is going to 1. Okay, so going to infinity is done not quite along geodesics, but modulo this kind of slowly growing function, you can imagine it's like on a geodesic. And you should think of this Gromov product. So this Gromov product is the same as the I should probably point that out first. This Gromov product. See, I can translate. This is the same. I can translate by Wm. All of these. So this is the same as x0 dot Wm is the same as Wn x0, and then the base point is Wm x0, right? So that's really, you should think of it as the distance between this point and the geodesic between x0 and Wn x0. Okay, so I don't know. The proof of this is maybe a page, but maybe I'll skip it. Okay, so now we get to the hyperbolic geometry fact. So I have 4 points in x. X is delta hyperbolic. And I assume that these Gromov products are big. Both of these are bigger than some number a. And a dot c is much less. It's less than or equal to a minus, say, 10 delta. Okay, then a dot c and b dot d are close. I don't know, I have 200 delta, but that's very generous. Okay, so the picture is here is x0, and then you have, let's see, it's like this. Right, so AB, so this quantity here, this is roughly the distance between x0 and this point, right? That's my number that's big, and this is another number that's big. But the number that's much smaller is the number here, right? That's the number that's smaller. This number here. This is the A dot C. And then the conclusion is that the BD number, well, in this picture, in the 3, they're exactly equal. But in the hyperbolic space, they're off by some number of deltas. Okay, so that's the hyperbolic geometry fact. And now, actually, this lemma, I think you should think of it as basically two independent random walks. You know, this one is running in reverse. This is like this mu hat random walk, and this is our mu random walk, and they're independent. They don't, you know, even though the indices are the same, they're using different g's. These g's are independent. You know, the g's here are completely independent from the g's here, and I think this lemma should be stated or thought of as, you know, it's the same statement but for two different random walks, not just these two particular ones, but any two different, you know, random walks still satisfy this. That's what the proof shows anyway. Okay, so now I want to apply this to the following. So C is that point, D is Wn x0, A is um inverse x0, and B is Wn inverse x0. Okay, so my tree here is like this. This is the base point, and then I have um inverse x0, and I have C is Wm x0, this is Wn x0, and this is Wn inverse x0. Okay, so notice that this distance here is growing linearly. That's the drift statement. Because you know, I'm looking at the usual random walk where Wm is, you know, this is the distance between Wm x0 and the geodesic between x0 and Wn x0, and that's sublinear by this lemma. So that distance is small, but the distance between x0 and Wm x0 and Wn x0, this grows linearly, right? So this blue thing is growing linearly then. Right? This is nearly a geodesic between x0 and, you know, x0, Wm x0, Wn x0. The modulo of this sublinear growing function is like a geodesic, and the length of that geodesic is linear in n. That's what the drift argument says. And the same thing over here. This is the same thing but with the inverse random walk. So this is also growing linearly. But this thing here. This thing here is growing sublinearly. That's well, it's so unfortunately I couldn't get the indices to cooperate. But you know, so here it's inverse and Wm, and in the lemma it's Wm inverse and but it's the same thing. It's like reversing the random walk. So this lemma also applies if I put the inverse over here. Right. So this is sublinear. This is less than or equal to L of n, while these blue things are growing linearly. So I'm certainly in this statement inside this fact here, where these distances are much bigger. You know, these two distances are much bigger than the A dot C. And so then I conclude that B dot D is also small. It's you know, it's up to 200 delta is the same as this. So I conclude that. So the conclusion here is that you know, Wn inverse x naught dot Wn x naught this is less than or equal than I don't know, L of n plus 200 delta with probability going to 1, right? Okay, so that's one thing to remember. And then we have another hyperbolic geometry fact, or we can call it a lemma. I was calling it the final lemma here, but it you know, it is another hyperbolic geometry fact. It's that so G is some isometry of x, and the distance between the base point and G of the base point is at least 3 times this dot product, the Gromov product here, plus 20 delta. Okay, then G is loxodromic. And the translation length of G is greater than minus 2. Okay. So why is this, right? You have, just a quick picture. Here's x0, here's maybe G inverse x naught, here is G x naught. What this inequality is saying is that, x0 is pretty close to the geodesic from G inverse x0 to G of x0. This distance, the dot product between these two is, much less than the distance between x0 and G of x0. So this, you should think of this as being large and this is small. And in fact, we have much more over here. The distance, this is my x naught. This thing here is the yellow bit. That's this L of n that's growing sublinearly, and my G is Wn, right? My G is Wn. So this is linear in n, while the distance over here to that geodesic is sublinear in n. So it's much more is true in our situation than what the lemma requires. But you should think of it as being, this is much smaller than the distance between these two. And what that means is that if I look at the orbit, so I have x0, I have G of x0, I have G inverse of x0. Where is G squared of x0? Well, I translate this whole picture by G, right? So I'll have, I don't know, here's G. Right, this Gx0 should be very close to the geodesic between x0 and G squared of x0. So what you get is when you iterate, you get a quasi-geodesic. You get, local quasi-geodesic implies global quasi-geodesic, where you have to insert your constants. But this is almost, right, this is almost a geodesic, except for this little bit. It's almost a geodesic. So when you start translating around, you get a quasi-geodesic that the G translates. So G is loxodromic. And its translation length is, it's roughly equal to this distance. I mean, a little bit less, maybe. And that's what the lemma says. And so there you have it. That's it. Because here we know that the distance between these two is linear in n, right? Because the distance from Wn x0 to x0 is linear in n, and these Wn and Wn inverse are sort of on opposite sides, right? When you draw the geodesic, x0 is very close to the geodesic. So it follows, right? So you're done. I don't know if it's clear from what I said, but the point is this is growing. This is when G is equal to Wn. This is growing linearly, and this is sublinear. And so this whole thing is bounded below by some linear function, and that was the statement. Okay, so this is nearly perfect. I skipped some proofs, but maybe you don't want to see them. All right.
Okay, any questions?
Actually, does this say that if you divide this by n, this should converge to the same eta? Because tau of G is also trivially bounded from above by this distance, right?
Oh yeah, you're right. Yeah, I think that's probably right. Yeah. So I divide by n, I get the same. So it's the same as the drift.
Yeah.
Same as the drift. No, that's a good point. Mm-hmm.
Any other questions? No? I don't have less thanks our speaker.